This is the second part in our series of how to build the world's fastest car with Bloodhound SSE. In the first part, we looked at the design, the chassis and the monocoque. And if you missed that video, check it out at the end of this one. There'll be a link at the very end. Dan, you showed us around the chassis, the monocoque. I want to now know what goes on inside Bloodhound.
Well, Andy's going to have to start the car to get it to run. So the best person to talk about starting the car and the engines and how you control it is probably Joe. So if I can hand you over to Joe, who's our systems engineer.
Come on in, Joe. Thank you very much, Dan.
Hello.
Hello, Joe. You're systems engineer on Bloodhound. Yeah. So I want to know, it's empty at the moment, but I'm guessing some engines are inside Bloodhound. Where are they?
Yeah, there's three main engines. We have a jet, which sits up here in the upper chassis. That's the intake for it. We have a Formula One engine, which sits in this space here, and also a rocket engine, which sits in the space at the back here.
So it's looking very empty. Are the engines ready?
Yep, I can show you an EJ200 if you like.
Perfect.
Okay.
Let's have a look. So here it is, a real-life jet engine.
Yep, this is an EJ200 taken from a Eurofighter Typhoon fighter aircraft.
So you've got three engines in Bloodhound. What happens first? How does Andy start the world's fastest car?
Okay, so the jet engine gets started first, and that's done via something called a ground start car. That provides compressed air to the engine and spins it over, and then when it gets to a certain speed, it will come under its own power. At that point in time, we then take electrical power and hydraulics off this engine, which supply the rest of the car. Andy will control the jet throttle from inside the cockpit from a pedal on the floor, just like a normal accelerator in a car. And he'll take the car to about 350 miles per hour before engaging the rocket. The jet itself alone is capable of producing 9 tons of thrust, which is about, if you could, 60,000 horsepower.
Okay, and so what fuel are you using in the world's fastest car?
Normal jet fuel for the jet engine, and then for the Formula One engine, it's just unleaded, and then
just unleaded, like you would have in your car on the road?
Just normal unleaded, yeah. And for the rocket, it's something called high test peroxide.
And so the overall horsepower, what are we talking?
135,000, which is about 180 Formula One cars.
That is a lot of F1 cars,
Yeah.
My goodness. So we've seen the engine, we've seen the outside of Bloodhound. I'm guessing it's the world's fastest car for a reason. It's going to have wheels. Where are they and how many?
There's two types of wheels. There's ones for the runway tests and there's ones for the ones in the desert. We've got the runway ones here if you'd like to take a look at them.
Certainly would. Let's go and have a look.
So these are the UK runway wheels that we use for runway testing here.
And they've got rubber.
Yeah, that's right.
Is this what you're going to use for Bloodhound with the world's fastest car?
No. These ones are rated up to about 200 miles an hour. The ones in the desert will be solid wheels.
Solid
aluminium.
Aluminium, okay.
Yeah, an aluminium alloy, basically.
And that is that just because of the speed? Is it because of the area?
It's because of the speed. I mean, the G's at the tips of the wheels in the runway are in the desert wheels at 1,050 miles an hour, about 50,000 G. So the stresses on the wheels are fantastic. So these wouldn't survive it, basically.
My goodness, that is a lot of pressure. And they have to be used, the same wheels for both runs, for the record?
So it depends on how much damage we pick up during the run. I mean, the aim is, just to keep the original ones on there if we can, but we'll have to inspect the wheels post-run just to check if they've taken any damage.
Well, now I have seen the world's fastest car, the engines, the wheels, the chassis, the monocoque. I kind of want to know how we stop this thing when we're at top speed at 1,000 miles per hour.
That's the important bit, yeah.
I think I'm going to head back over there to see Dan.
Okay.
Thank you very much.
Bye.
Dan, I'm back. We have got to 1,000 miles per hour. We've seen the engines. I've seen the wheels. But I said to Joe, I want to know how to stop Bloodhound.
Yeah.
What happens?
Very good question. So we've spent all this time making the aerodynamics of the car really, really slippery to accelerate it to 1,000. Of course, then we have to stop it, which is an equally difficult challenge. So the first thing Andy will do is he'll actually switch off the engine so that the power will go. And the natural drag of the car will actually start to slow it down at about 3G. That won't be enough, so we actually have the first of 3 braking systems he'll operate. So at about 850 miles an hour, he'll open the air brake doors,
Where are they?
They'll be on this structure here. This will be the hinge line. So this cutout is for one of the brackets.
Okay,
So
we've got a little miniature of Bloodhound. I think, is this, so we're probably around here. Are these the doors?
Yeah, that's correct. So this area here, as you can see, this pattern of holes. So the doors will literally open out to about this angle, which basically increases the cross-section area of the car, therefore increases the drag of the car, so it actually brakes the car harder. So it's an aerodynamic braking device, if you like. The holes are in there just to actually relieve some of the pressure on there. So these doors actually will hopefully provide most of the braking efficiency we're looking for over the 4.5 miles we've got to stop the car.
And then there's no sort of foot brake?
There are wheel brakes. It's when we get down to below 200 miles an hour, then we can actually use conventional wheel brakes, so discs and pads, but just quite big ones. The reason we can't actually use wheel brakes earlier than that in the higher speed range is because we use solid aluminium discs as wheels, and it's a very low coefficient of friction on the desert, so there's very little traction. So if you applied the wheel brake earlier, you just lock the wheels and just slide. So you wouldn't actually get any braking. But as the car slows down, the weight of the car and the actually it's sat lower, if you like, in its ride height, and there's more ground interaction. So we can actually use the brakes to stop it, or Andy can stop it in a prescribed area that he needs to stop in.
So you've got wheel brakes, you've got the door brakes. If those don't potentially work, is there anything else on board?
We do actually have 2 parachutes as well. As you can see at the back of this model, we have 2 parachutes.
Oh yes, look at those, they're all just neatly packed in.
So we originally schemed the car to brake using 3 braking devices, be it the air brake doors initially, then parachute braking, and then wheel brakes. But we found that the air brake doors might actually give us enough braking efficiency, so we'll leave the parachutes actually in the design, because we always need to consider safety and reliability. So either one of the 2 parachutes will also stop the car, so we've got redundancy built in for Andy's safety.
So Andy's definitely going to be able to stop this car.
Yes.
From 1,000 miles per hour down to 0. I'm still having trouble getting to grips with the fact that you can find out everything about Bloodhound SSC. If you want to try and build your own world's fastest car, log on to bloodhoundssc.com and have a go yourself.
So Andy's office is actually probably one of the first things we have to actually get in place, because everything else is bolted to it.